Usually when we think about modern medicine, we picture uh, surgical precision.
Right.
Yeah,
Exactly, like a mechanic.
right, like a specialized mechanic fixing a car, a belt snaps, you pull out the broken belt, you slot a new one in, and, well, the engine purrs. The problem is isolated, and the fix is clean.
We really crave that kind of containment. It's comforting, to believe that when something goes wrong in the human body, we can just surgically remove the bad part and leave everything else completely untouched.
But when you step into the world of oncology, and specifically the history of treating cancer with chemical drugs, that mechanics toolbox it goes out the window.
It really does, completely.
Today, we hear a lot about new treatments like targeted therapies, which operate a bit like, say, changing the locks on a single door so the cancer can't get in.
Right, highly specific.
But classic chemotherapy, the foundational drugs that still make up the vast majority of cancer treatments, that is a very different beast. It is much more like flooding the entire house just to drown a single termite.
Wow. Yeah, that is a brutally accurate way to describe it. It's the ultimate systemic high-stakes trade-off. You're basically saturating the entire system to eliminate a microscopic threat.
And that systemic trade-off is the focus of our deep dive today. We've got a fascinating stack of pharmacological sources in front of us, unpacking a medical reality that will touch roughly, 1 in 2 people in high-income countries at some point.
Which is a staggering statistic when you think about it.
It really is. So we are looking at cytotoxic chemotherapy. Our mission today is to decode how these drugs actually work.
Yeah.
We're going to explore their truly wild origins, break down the biological machinery they attack, and understand the brilliant and occasionally catastrophic logic behind how oncologists strategize with them.
And stripping away the mystery of these drugs is just so important because for anyone listening who has been touched by this, the sheer complexity of a treatment plan can feel completely overwhelming.
Okay, let's unpack this by defining our terms, because the word chemotherapy gets thrown around constantly. Like if you walk into a clinic today, patients, and even a lot of nurses and doctors will casually refer to almost any IV cancer drug as chemo.
Yeah, they do.
But our sources point out that oncologists actually bristle at this. Why does blurring that terminology matter so much?
Well, it matters because words dictate our understanding of mechanism. The term chemotherapy was actually coined way back around 1900 by a German scientist named Paul Ehrlich.
Okay.
And he used it to describe literally any chemical treatment for any disease. His big breakthrough was an arsenic-based drug called salvarsan, which was used to treat syphilis.
Oh, wait, so it literally just meant chemical therapy and had nothing to do with cancer at the time.
Precisely, yeah, nothing at all. But by the mid-20th century, the medical world narrowed the term to mean cancer drugs specifically.
Right.
But today, the field has specialized so heavily that we have to draw a hard boundary between classic cytotoxic chemotherapy and all these newer treatments.
Cytotoxic meaning literally toxic to cells.
Exactly. These classic drugs are specifically designed to poison rapidly dividing cells. They indiscriminately break the machinery of cell division.
As opposed to the newer drugs, which do something entirely different, right?
Right. Like if a patient gets an immunotherapy drug, that drug isn't poisoning a dividing cell at all. It's taking the brakes off the patient's own immune system. Or if they get a targeted therapy, that drug is hunting for one specific mutated protein on a cancer cell.
I see.
So if you lump them all together as chemo, you completely lose the ability to understand why the side effects are so radically different. An immunotherapy drug doesn't usually make your hair fall out, but it might cause an autoimmune reaction. The underlying mechanism is everything.
Which means if we want to understand the collateral damage of classic chemotherapy, we really have to understand its mechanism. And to understand the mechanism, we have to look at where these drugs were born. I was reading through the historical section of our sources, and the origin story doesn't start in a sterile medical lab. It starts in the middle of a war zone.
It really is arguably one of the darkest, strangest pivots in the history of science.
Yeah.
The origin of chemotherapy is inextricably linked to chemical warfare.
Here's where it gets really interesting. Let's set the scene, because this is wild. World War I. Soldiers in the trenches are exposed to sulfur mustard gas. The immediate effects are obvious and horrific, blistering of the skin and lungs.
It was awful stuff.
Right. But medical observers looking deeper noticed a secondary internal effect. The gas caused severe suppression of the soldiers' bone marrow and lymphoid tissue.
And the bone marrow is essentially the factory where all your blood cells and immune cells are manufactured. So the gas was shutting that factory down entirely.
Wow.
But for about 2 decades, that observation was just a grim footnote in military medical texts. Nobody really knew what to do with it.
Right. Until December 1943, World War II. The Bari Harbor disaster in Italy. A German air raid attacks the harbor and sinks an American cargo ship called the SS John Harvey.
What the Germans didn't know, and actually what almost all the Allied sailors in the harbor didn't know either, was that the John Harvey was secretly carrying a massive classified payload of mustard gas munitions.
Unbelievable. So as the ship goes down, this chemical payload mixes into the water and the air. Hundreds of servicemen and civilians are suddenly exposed. The U.S. Army dispatches a brilliant physician named Stuart Alexander to investigate this mass casualty event.
Yeah, and Alexander begins autopsying the victims, and he zeroes in on their blood. He documents that their white blood cell counts, specifically their lymphocytes, had just completely collapsed.
So the mustard gas was systematically hunting down and wiping out these specific, rapidly dividing immune cells.
Exactly.
And here's the staggering leap of logic. Alexander looks at this catastrophic chemical weapon and thinks, well, what if we could harness this?
Right. Such a bold thought.
Yeah, like if this gas is so incredibly efficient at destroying lymphoid tissue, could we use it to kill cancers of the lymph system?
He realized the weapon could actually be aimed. And his findings fed directly into top-secret military research happening at Yale University. Pharmacologists Louis Goodman and Alfred Gilman, who were working under a wartime contract, were studying these nitrogen mustard compounds.
Okay.
And in 1942, they partnered with a thoracic surgeon named Gustav Lindskog. They actually took a nitrogen mustard compound and administered it intravenously to a patient with advanced non-Hodgkin lymphoma.
The very first modern chemotherapy treatment. What actually happened to the patient?
The patient's massive tumors shrank dramatically. I mean, they almost disappeared.
That's incredible.
Now, we have to be clear, it was only temporary. The tumors eventually adapted and returned. But conceptually, it proved that a systemic chemical could melt away a solid tumor mass.
Right.
But because it was classified military research, they couldn't publish a word about it until 1946, after the war ended.
So the literal foundation of oncology is a repurposed chemical weapon.
Yeah.
But our sources highlight a second foundational moment happening almost simultaneously, taking a completely different approach. Boston, 1947. A pathologist named Sidney Farber is treating children with acute lymphoblastic leukemia.
And Farber was approaching cancer not through toxins, but through nutrition and biochemistry. He was studying folic acid, a B vitamin that is absolutely crucial for the synthesis of DNA and cell growth.
He theorized that giving these children massive doses of folic acid might cure them, but why would he think feeding a tumor a growth vitamin would help?
Well, he was looking at the severe anemia these leukemia patients suffered from. He thought that if he could just stimulate the bone marrow to produce normal, healthy red blood cells, it might somehow crowd out or overpower the leukemic cells.
But the reality was horrifying, right? It acted like pouring gasoline on a fire. The leukemia accelerated, and the cancer grew faster than ever.
It did. But that devastating failure provided the biological key. He realized if folic acid fuels the cancer's explosive growth, the logical inverse must be true. What if we starve the cancer of folic acid?
Oh, wow.
So Farber collaborated with a brilliant chemist named Yelapragada Subro, who had actually managed to synthesize a folic acid antagonist.
An antagonist meaning a molecule that blocks the body from using the vitamin.
Exactly, a drug called aminopterin. Farber took this blocking agent and administered it to children whose leukemia was considered totally terminal.
And it induced miraculous remissions. He basically founded pediatric oncology right then and there.
He really did.
Looking at both the Yale mustard gas trials and Farber's folic acid blocker, it feels like a game of biological judo, you know?
Good way to put it.
Yeah, in both cases, scientists took the momentum of the enemy, the destructive power of mustard gas, or the ravenous, cancer-fueling appetite for folic acid, and they just flipped the opponent's own weight against them to defeat the disease.
That analogy holds up perfectly. You are exploiting the very mechanisms the cancer relies on to survive. And these early discoveries laid bare the fundamental vulnerability of all cancers. They divide rapidly, and they divide chaotically.
Which perfectly transitions us to the core logic of how modern chemotherapy is designed. Once researchers knew cancer's main weakness was its chaotic division, they started hunting for the choke points of that process.
Right.
To help visualize this, let's look at cell division as a massive high-speed factory. The factory's singular purpose is to assemble and accurately copy a gigantic, incredibly complex instruction manual, your DNA.
What's fascinating here is that the 5 major classes of cytotoxic chemotherapy we use today are essentially just different specialized tools used to sabotage that specific factory. And the sources break down the wildly different ways each drug class creates a catastrophic failure on the assembly line.
Let's walk through that factory then. The first class of drugs are the direct descendants of those Yale mustard gas experiments, alkylating agents. How do these sabotage the manual?
So alkylating agents act like industrial superglue. They attach reactive chemical groups directly onto the DNA strands. The sources note they create covalent bonds, crosslinks, that literally fuse the 2 strands of the DNA double helix together.
Hold on, I want to make sure I understand the chemistry there. What makes a covalent bond so devastating to the cell?
Well, a covalent bond is one where atoms share electrons. It is an incredibly strong, tight chemical bond. Think of it like spot welding 2 pieces of metal together.
Oh, okay, got it.
The DNA helix is designed to be easily unzipped so it can be read and copied. But when an alkylating agent creates a covalent crosslink, it welds the strands shut.
So when the factory machines try to pull the manual apart to read the pages, they just can't. The pages are glued together.
Exactly. And when the cell's internal damage detection system scans the DNA and sees this unrepairable weld, it triggers a process called apoptosis, programmed cell death.
It kills itself.
Yeah, the cell hits its own self-destruct button rather than passing on broken DNA. A classic example here is cyclophosphamide, which is fascinating because it's actually a prodrug. It is completely harmless when it enters your vein.
Wait, really?
Yeah, it only becomes a toxic DNA-gluing weapon after it passes through your liver and your liver enzymes metabolize it. We also include platinum-based drugs like cisplatin in this category because they cross-link the DNA in a very similar superglue-like way.
Okay, so if the first class is superglue, the second class is Sidney Farber's legacy. The antimetabolites. These don't glue the manual shut. They are molecular decoys.
They are counterfeit raw materials. They look structurally almost identical to the natural building blocks your body uses to make DNA or RNA.
The sources mention a drug called 5-FU that mimics a nucleotide. For those of us who haven't taken biology in a while, what is a nucleotide and how does a fake one kill a cell?
Nucleotides are the literal letters of the DNA alphabet. You know, the A, C, T, and G. They are the individual rungs on the DNA ladder. 5-FU looks exactly like a normal letter. So the factory assembly line grabs this fake building block and inserts it into the new DNA strand being built. But because it's chemically faulty, the whole structural sequence collapses.
So it's like loading the factory's printing press with invisible ink or like a faulty gear. The manual gets printed, but it's pure gibberish.
That's it. Methotrexate works in this class too by blocking the enzyme that regenerates folate, which completely shuts down the supply chain for new nucleotides. But there's a massive biological catch to this class of drugs.
Right, they are cell cycle specific.
Yes. They only work if the cell is actively trying to copy the manual. If a cancer cell is in a resting phase, just sitting there, antimetabolites are completely useless. They only do damage during the synthesis phase. Whereas our first class, the alkylating superglue, can weld the DNA shut whether the cell is resting or dividing.
Okay, so that's the manual. What about the machinery of the factory itself? The third class we read about are the plant alkaloids, or mitotic inhibitors. These don't target the DNA manual at all.
Right, they target the conveyor belts. When a cell divides, it creates these microscopic cables called microtubule spindle fibers. Their whole job is to physically attach to the chromosomes and pull them apart into 2 new cells.
And nature has provided us with some terrifying ways to break those cables. There's a drug called vincristine, derived from the Madagascar periwinkle plant. It binds to the proteins and stops those spindle fibers from ever forming. The cell tries to divide, can't build the cables, gets stuck, and dies.
Then you have paclitaxel, widely known as Taxol, which actually comes from the bark of the Pacific yew tree, and it takes the exact opposite approach.
How so?
Taxol allows the spindle cables to form, but then it essentially crystallizes them. It permanently locks them in place. The cell overstabilizes. It needs to disassemble those cables to finish the division process, but it can't.
Stopping the cables or freezing the cables both just completely break the factory.
Exactly.
Okay, moving to the fourth class, things get even more sci-fi here. Anti-tumor antibiotics. Usually an antibiotic cures, a sinus infection, but these are heavy-duty cancer drugs derived from soil bacteria.
Mostly from a genus of bacteria called Streptomyces. In the wild, bacteria wage these microscopic turf wars by secreting toxins to kill off competitors. We have essentially harvested those ancient chemical weapons.
The sources describe a drug called bleomycin using oxidative free radical chemistry to chop DNA to pieces. Again, let's translate that out of the textbook. How does a bacteria toxin physically chop up human DNA?
Well, a free radical is a highly unstable molecule that is missing an electron. Because it's unstable, it acts like a microscopic buzzsaw, violently ripping electrons away from anything nearby to stabilize itself.
Yikes.
Bleomycin binds to the DNA, reacts with iron and oxygen, and generates a localized storm of these free radicals. It literally shreds the DNA strands into pieces. And another drug in this class, doxorubicin, just physically wedges itself between the DNA base pairs, warping the entire shape of the helix until it snaps.
Nature is brutal. Finally, the fifth class, topoisomerase inhibitors. DNA is a massively long molecule tightly coiled up to fit inside a cell. To read it, the factory has specialized untangling enzymes, topoisomerases, that temporarily snip the DNA strand, let it unspool, and then seamlessly tape it back together.
And these drugs are brilliant. They trap the untangling enzyme right in the middle of the act. They wait until the enzyme has cut the DNA, and then they paralyze it before it can repair the cut. They turn a temporary, perfectly normal snip into a permanent, fatal break in the genetic code.
Understanding these 5 distinct mechanisms, the superglue, the decoys, the machinery blockers, the bacterial buzzsaws, and the untanglers, it really shows why oncology changed so rapidly.
It was revolutionary.
The sources point to Lawrence Einhorn at Indiana University in the 1970s. He utilized cisplatin, that platinum-based superglue drug, to treat metastatic testicular cancer. Before Einhorn, advanced testicular cancer was overwhelmingly fatal. But by attacking the perfect biological choke point, he turned it into a highly curable disease. Lance Armstrong is obviously the most globally famous example of that specific cure in action.
It was a total watershed moment. It proved that systemic chemical destruction, if aimed at the precise vulnerability of the tumor, could completely eradicate a metastatic disease.
I do want to circle back to something we mentioned a moment ago, though. Taxol comes from the yew tree, vincristine from the periwinkle flower.
Yeah.
They sound lovely. There is this pervasive narrative in wellness culture today that natural means gentle, or that if it comes from a plant, it is inherently safer than a synthetic chemical.
Looking at the pharmacology of these plant alkaloids, that misconception is not just wrong, it is incredibly dangerous. The natural origin of a compound has absolutely zero bearing on its toxicity.
The sources detail how intensely toxic Taxol is. When it was first discovered, they didn't know how to synthesize it in a lab. To treat just one single patient, they had to harvest and strip the bark off of 3 to 6 mature, decades-old Pacific yew trees.
They nearly drove the species to extinction before developing a semi-synthetic production method. If we connect this to the bigger picture, the toxicity of these natural plant toxins is staggering, and it leads us directly to the foundational flaw of every single drug class we just talked about.
The selectivity problem.
Yes. Cytotoxic chemotherapy is entirely blind.
Let's unpack that. When you say blind, you mean the drugs circulate through the blood, but they don't actually know what a cancer cell is.
They have no idea. All they know is how to attack a cell that is actively dividing. They cannot distinguish between a malignant tumor cell dividing out of control and a perfectly normal, healthy cell that just happens to divide quickly as part of its normal life cycle.
And this realization completely demystifies the side effects of chemotherapy. When people think of chemo side effects, the hair loss, the brutal mouth sores, the gastrointestinal nausea, the immune system crashing, we tend to think of those as unfortunate, random allergic reactions to a harsh drug.
But they aren't random at all. They are the direct, inescapable mechanistic consequence of flooding the house. Think about the fastest renewing tissues in the human body. Your hair follicles divide constantly.
Right.
The mucosal lining of your entire gastrointestinal tract, from your mouth down through your gut, replaces itself every few days. And your bone marrow is perpetually churning out new white blood cells.
So because those healthy tissues are dividing the fastest, they accidentally step right into the crosshairs of the drug. They take the hardest hit from the superglue and the decoys.
It is collateral damage in the purest sense. And it imposes hard, terrifying limits on how oncologists can treat a patient. Our sources highlight specific lifetime toxicity thresholds.
Right.
Doxorubicin, the bacterial drug that warps the DNA, can only be given up to a very specific cumulative lifetime dose. It doesn't matter if it is actively melting the tumor away. If a doctor exceeds that dose, the risk of irreversible fatal heart failure skyrockets.
Wow. And bleomycin, the free radical buzzsaw, carries a severe risk of permanent pulmonary fibrosis, literally scarring the lungs. And perhaps the most agonizing trade-off. Some of the older alkylating agents, the descendants of the mustard gas, damage the DNA so aggressively that they can actually cause healthy cells to mutate into secondary leukemias years or even decades after the patient was successfully cured of their original cancer.
The cure itself seeds a future disease. It is a razor-thin therapeutic window.
So what does this all mean? Given everything we just covered, these brilliant mechanisms paired with this brutal, blind toxicity, how do doctors actually use them? Like, why is a patient told they need to come in for cycles of chemo, getting 3 or 4 different drugs at once, instead of just getting one big dose to wipe it out?
The strategy is dictated by 2 foundational mathematical models in oncology. The first is the log-kill hypothesis. This model states that a given dose of chemotherapy doesn't kill a set number of cancer cells. It kills a constant fraction of them.
Oh, so it's not one dose kills 1 million cells. It's one dose kills 99% of the cells.
Correct. So if you start with a tumor made of 1 billion cells, the first dose kills 99%. You still have 10 million cancer cells left.
But because of the toxicity to the gut and the bone marrow, the doctor has to stop.
They have to wait for the patient's healthy tissues to regenerate. Once the patient recovers, they hit them with a second cycle. That cycle kills 99% of the remaining 10 million. It is a calculated war of attrition, grinding the tumor population down fraction by fraction until the patient's own immune system can mop up the stragglers.
That perfectly explains the cycles, but why the combinations of different drugs?
Well, that brings us to the Goldie-Coldman hypothesis, which deals with cancer's ability to evolve. Tumors are genetically unstable. They mutate constantly. The mathematics dictate that by the time a tumor is large enough to be detected on a scan, the probability approaches 100% that it already contains a subset of cells that have randomly mutated a resistance to whatever drug you are planning to use.
So if a doctor just gives the patient class 1, the superglue, it might melt away 99% of the tumor. But those few mutant cells that are immune to superglue survive, multiply, and suddenly the entire relapsed tumor is invincible to that drug.
Exactly. This is why combination therapy is essential. You have to strike with multiple non-cross-resistant drug classes right out of the gate. You hit them with the superglue, the decoys, and the spindle blockers simultaneously.
Because mathematically, it is extremely unlikely for a single cancer cell to simultaneously mutate a defense against 3 completely different mechanisms at the exact same time.
Vincent DeVita proved this in the 1960s with a regimen called MOPP. He combined 4 different classes of chemotherapy to treat advanced Hodgkin lymphoma, which was essentially a death sentence at the time.
Wow.
By attacking 4 different choke points at once, he pushed the majority of his patients into durable long-term cures.
It revolutionized the entire field. But I have a question that seems, obvious. If combination therapy works, and the main threat is a few resistant cells escaping, why not just obliterate the tumor on day 1? Why not just give a massive, overwhelming, nearly lethal dose of the drugs to guarantee every single cancer cell is destroyed immediately?
The medical community asked that exact question in the 1980s and 90s, and the answer is one of oncology's most tragic cautionary tales. The theory was called maximum tolerated dose. The logic felt sound. If a higher dose kills more cells, let's push the dose to the extreme limit of human biology.
The sources outline how this was applied to breast cancer. Doctors began giving extreme high-dose chemotherapy regimens that were so toxic they completely annihilated the patient's bone marrow. To keep the patients alive, doctors had to harvest their stem cells or marrow beforehand and literally rescue them with a transplant after the chemo cleared.
It was an incredibly aggressive approach, and it was heavily pushed by the public, too. Patient advocates fought for it. People sued their insurance companies to cover it because the intuitive logic just hit the cancer harder. Made so much sense.
But, and you're shaking your head right now, why did it fail? If you pour 10 times more poison on the tumor, why didn't it cure them?
Because it completely ignored the biological reality of resistance we just talked about with the Goldie-Coldman hypothesis. If a subset of breast cancer cells has mutated to become chemically invisible or resistant to an alkylating agent, pouring 10 times more of that same agent onto the tumor does not kill those resistant cells.
Oh, I see.
Yeah, it just massively destroys the patient's healthy organs, while the resistant cancer cells survive completely unharmed.
When they finally ran rigorous randomized clinical trials in the late 90s, The data was devastating.
It was. The extreme high-dose treatment did not improve survival rates compared to standard doses, but it caused horrific collateral toxicity and significantly higher treatment-related deaths. The cure was killing patients without stopping the cancer any better than conventional doses. It proved that a plausible biological theory simply cannot outrun rigorous clinical evidence. You cannot just brute force your way past the therapeutic window.
We have covered an incredible amount of ground today. To synthesize all of this, while the bleeding edge of medicine is rapidly advancing into targeted treatments and immunotherapies, classic cytotoxic chemotherapy remains the curative backbone for countless diseases. It is a diverse family of molecular wrecking balls, alkylating agents gluing the DNA, antimetabolites slipping and faking, plant alkaloids jamming the physical machinery, bacterial toxins acting as free radical buzzsaws, and inhibitors trapping the untangling enzymes, each designed to sabotage a specific vulnerability in the chaotic assembly line of a dividing cell.
And this raises an important question. Why does all this detail matter to you? Ultimately, this knowledge is about empowerment. When you or a loved one are sitting in a clinic facing a complex diagnosis, understanding these classes changes the entire conversation.
Absolutely.
It demystifies why the treatment plan isn't just one magic pill, but a carefully timed cycle of 3 different IV bags. It explained exactly why the hair falls out and the immune system drops. It replaces the paralyzing fear of the unknown with biological clarity.
It changes everything about how you look at the medicine going into the bath. I want to leave you with a final thought to mull over, circling all the way back to our origin story. The very first chemotherapy cures, the conceptual foundation for a medical field that has saved millions of lives, were born from the ashes of a tragic, classified World War II chemical weapons disaster in the waters of Bari, Italy. Stuart Alexander looked at a horrifying mass casualty event and found the seeds of a cure. It really makes you wonder, what other catastrophic modern industrial hazards or tragic environmental accidents happening right now around the globe might secretly harbor the foundational clues for tomorrow's greatest medical breakthroughs, just waiting for the right scientists to connect the dots?